Hi everyone, so in this video we will see how to pattern on insulating substrates. So when we pattern on insulating substrate, we face the problem of not being able to use the electrostatic force to bend our cantilever. So the electrostatic force is generated by applying a potential difference between this capacitive platform of the cantilever and the substrate. But if the substrate is an insulator, then we cannot easily accumulate charges on it. So we cannot have this nice potential difference that we use to bend the cantilever. So in theory, this may make you think, okay, I cannot pattern on insulating substrates, but that's not really true. There are some ways to do it, and one way that we often use is by what we call using the thermal bending effect. So we notice that when we heat up the cantilever, when we heat up the heater of the riser here, this also causes a bending of the cantilever, which is independent by the voltage that we apply to have this electrostatic force to bend the cantilever. For this reason, we can pattern also using zero force voltage, but just using thermal bending. So let's see how we can approach this situation. First, I will move to a sample. In this case, I will move to a sample with a thick PPA. So let's move here and we do a quick approach. So when we pattern with insulating substrates, we may want to pattern as for non-insulating substrates 2D or grayscale designs. So first we can see how to pattern a 2D design and also a grayscale. So if we want to pattern 2D design, we can import an arrow, for example. And in this case, I want to use it for TSPL. And I want a pixel size of 20 nanometers. I want this to be in 2D. Perfect. And let's put this to 1 maybe. Remove the scaling. And we put a depth of, say, 40. In this case, since we cannot use a force to pattern our, in this case, our arrow, then we cannot also use the feedback, because the feedback is acting on the voltage that determines the electrostatic bending. So the feedback is going to be useless. But I will just start a pattern with the feedback to find some parameters and also show you the difference between patterning with and without force and with the thermal bending. So let's say we're good with our design. I import it. So let's move here to our position. Let's check the configuration was okay. Oh, the tip seems quite non-sharp. Okay. Let's lift it. Okay, the adhesion length seems very large. It's probably, I will not recommend to write with this tip, but we can anyway try to see because this design has quite a low resolution, so it should be fine if the tip is still able to pattern. So we see that still this design is quite large. So first of all, I want to pattern in a standard way. So we use maybe Kalman feedback. We start with 5 volt. And in this case, I'm not patterning on top of an insulating substrate, but a normal silicon sample spin coated with PPA. But I just wanted to show you the difference between the two approaches. So in one case, I just start a pattern with a random initial force of 5 volts and the feedback with the Kalman. So we can see here that we are able to pattern this arrow. The adhesion length is still quite large, but maybe we're able to clean the tip a little bit when we do the patterning. But anyway, what we see is that we are patterning as expected this arrow. And in this case, we can see in the analysis, in the right forces, we can see which forces we're using to write this arrow. And the force is clearly non-zero. So we are bending the cantilever now because the substrate is not an insulating substrate. But what happens if we now disable the feedback and I impose a force of 0? Well, what we may expect is that since we're not using any force, then we are not going to see any arrow written. Because when we are on top of the surface, we are at 250 nanometers away, the forward height, and this distance is not going to be reduced by the bending caused by the electrostatic actuation. So as expected here, we see that we're not writing anything. We can also stop the patterning here. But what happens if we increase the temperature, let's say to 1200 Celsius, and we start this pattern again? We can also confirm on the analysis that the right forces here are 0. So as you can see, no force is being applied. So indeed, there is no bending of the cantilever. The writing is not really possible in the traditional way. Now I increase the temperature, let's say 1250, even higher. And this temperature may be high enough to allow us to see some effects of thermal bending. So let's check. And indeed, we start seeing some thermal bending, even at 1200. We can even do 1150 maybe, or 1100, or 1050. In general, what we see is that we are reducing the temperature here, and the patterning depth is decreasing, because the higher the temperature, the larger is the thermal bending effect. Here we probably had a cleaning event, and we changed the conditions of the tip a little bit, but clearly here we can see that by reducing the temperature, we are also reducing the patterning depth. So just to check again, here the force is 0, but we are writing. So we can use this effect to write some designs. One question that you may ask yourself is, why are we writing a square and not an arrow? Well, that's because our geometry is within a square, and we start turning on the heater from the left to the right of the writing field. So even here, for example, the heater is on, but we are not applying any force. So basically the condition is the same here or here, whether it's black or whether it's white. So this is why we are obtaining an arrow. Is there a way for us to obtain an arrow? Well, the answer is yes. If we use a temperature map, we can import a temperature map with the same shape of the design that we have. So in this case, we have this arrow. We import temperature map at 1150. Sorry to import it again. At 1150. We resize it and add to the target field. So now I can move a little bit, and I have to select the temperature map and write it again. Basically, now the temperature that we use is the temperature that we set in a temperature map, so 1150, and we were able to see that here this temperature was allowing us to write into the PPA. I'm using 0 force, and by using the temperature map, we will turn on the heater of the writer only in the areas that are marked by the temperature map. So we can see that we're writing with a depth of 20 nanometers into the PPA. Depth is a little bit changing because the tip was probably contaminated a little bit. We see that the adhesion level now is changing quite a lot. Probably we got rid of contaminations here. So the tip is not in the best shape, but at least we're able to see what I wanted to show you, which is that we are now writing the arrow without using any force. Again, let's check it just so that you believe me. In a substrate which can be an insulator. So in case you want to write something in grayscale, the approach would be pretty much similar. So let's say we want to write a sine wave. Sorry, I have to import the sine wave firstly here. Don't want it in 2D, I want a sine wave. And I put okay. And this is the design of the force that I'm importing. But as we know, I'm not going to use a force. So the fact that this is a sine wave or it's an arrow doesn't really matter that much, right? Because this force design is not going to be applied on by the electrostatic actuation because we have an insulating substrate. So this is more for a visual help. Now, on top of this new design that we are importing, we apply temperature map. And let's say we want to apply it between 1250 and 1000. Why not? And we resize it and add to this target field. Now I select the other field. And the force is again disabled. So no voltage is bending cantilever. Maybe I make the scan height a little bit larger because I don't know how deep I'm going to write. And the temperature that we're applying is between 1000 and 1250. In this case, when we are using temperature map, we are not using any feedback. So the only feedback that we can use is ourselves. So we have to check after applying a certain temperature map how the pattern looks like. Then we can tune it manually to make it look a little bit better and make it conforming to our design. So in this case, we see that we are not really, I mean, we're patterning much deeper than expected. So for example, we can stop it. And we can see that actually it was here. So we can see that when we are patterning in at the peaks of the sine wave, we're not patterning deep enough. So the target will be around 15. But when we want to pattern in the deepest side is around 45. So what can I do is modifying the lower temperature. Maybe instead of 1000, I can put 1050, but also modifying the upper temperature because it's too high. So I put 1050, and maybe here I put 1190. So now we should write not so deep at the deepest part of the sine wave, so here, but also we should write a little bit deeper at the top part of the sine wave. And then, as expected, we're patterning a little bit deeper. This height of the top of the sine wave is pretty much okay. The bottom part is still very deep. So maybe I can stop it again. Here you see that the design is not matching with our target, but in the end, this doesn't really matter if I just invert the sine wave here. It will look probably better, but it's just, again, visual aid because this force design is not going to be applied because we're not using any force. So now you see that the yellow part is where we apply the highest temperature, so also corresponds where we should apply the highest force, but again, the force is not being applied because the force is 0. So just for a more, so for better looking sine wave, we can use this design too, maybe. But as we said, we're still patterning too deep. So let's put maybe 1130. And let's launch it again. Again, let's not forget to always use temperature map whenever we are using temperature maps, otherwise it will not be applied. So now we should also see that the top of the sine wave should also match with the top of the field that's patterned by the temperature map, because I inverted the design in the geometry. Okay, so here we see already something a little bit different, but for sure, at least we see that the bottom is matching with the bottom. And again, the patterning, especially in grayscale with thermal bending, is a little bit tricky. It's not very straightforward, and we don't have a feedback at the moment. So it requires some tuning. Probably here I would increase again the temperature here. Probably will also have some cleaning event that is changing the condition of our tip. So in this case, we have a good match, but we're also depending a lot on the possible contamination. The fact that we also use temperature instead of force pulse to bend the cantilever makes the bending not so efficient, and also may cause increase of contamination when we pattern. In this case, we can already see that here the result is not so bad, and we have to remember that we are not using any force. This is just temperature without any sort of feedback. So as a preliminary result, probably I would say not so bad. Let's say if we can make it again a little bit better, this will be a very fine tuning, probably a little bit more temperature and upper level, and lower temperature in the lower level. Let's see, let's do this last try, and see if we can get a slightly better result. But anyway, we saw that we can pattern without force. So always see the pixel-wise right forces to actually believe the fact that I'm not using any force to write on my substrate. This is a technique that should allow you to write on insulating substrate. We also have to keep in mind that our tip was not probably the best tip ever, because we accumulated some contaminations here. Maybe with a tip cleaning, it could get better also. But patterning in grayscale with the temperature map is definitely not an easy task. So keep that in mind. You have to be patient when manually tuning the parameters. Hopefully in the future, we may have in the nanoFreezer software a temperature based feedback, so that it could help us in writing better on insulating substrate with thermal bending. But for the moment, this is the solution that I would recommend you to write on your samples if you want to write in 2D, or in grayscale. And we saw that the 2D is much simpler and more straightforward. 3D or grayscale requires more optimization. But at least this last part of the sine wave doesn't look that bad. And yeah, so this is pretty much it. So showing you how to pattern with the thermal bending on insulating substrates. We saw that we have to apply a temperature map on our designs, and remember to check temperature map here. And I hope this helped you on for your research for writing on this substrate, which are a little bit more challenging. But you can always do it, and I showed you in this video that it's possible and it's also not that complicated. Thank you for watching the video, and good luck.